Suppose you're working in NLP or AI like half of the world, including myself. You want to do some text cleaning to prepare training data for a multi-language model. Your goal is to remove text with duplicate meaning within each language. So you quote-unquote write a quick cleaning function, even dusting off the ancient language of regex that was once known to humans, but only spoken by large language models these days. You run the function on an example input. Looks like it's working as expected. But there's a bug in this function. Can you spot it? I'll give you a hint. It's not regex related. Can you spot the bug now? The whitespace and new lines are handled fine by strip and regex. The bug is caused by the string.lower method. These two words both mean street, but string.lower doesn't map them to the same lowercase string, so duplicates slip through our dedup. The fix is to use the string.caseFold method. It applies Unicode case folding rules designed for caseless matching. And now both versions match. Other languages have similar cases. For example, Turkish has a dotless variant of lowercase I and dotted capital I. Greek has two lowercase sigmas, same letter, different position in the word. Sometimes these differences are easy to overlook. In a wall of text, these two spellings look identical but aren't the same. The first uses a single Unicode ligature, the second uses two characters. OCR software and PDF extractors produce these frequently. Remember when I said the bug? I lied. It was actually a bug. There are more bugs in the code we thought we just fixed. But before we go hunting for them, let's talk about what we can do about these bugs. What we just did is called manual testing. We wrote the code, gave it some input, and checked whether the result was what we expected. The problem with our approach, even though we'll see that there's a better way, is that we did this by hand. We ran the function a couple of times with different inputs, fixed the code to make sure it worked, and moved on. What happens when we or someone else later changes the code back to using string.lower? In the best case, we find out by doing some manual testing again. In the worst case, we get silent failures. Imagine spending hours on compute to train your model, only to realize that your training data had duplicates the whole time. Manual testing doesn't scale. The better way is writing test code that checks your source code automatically. When you hear people say testing, this almost always refers to automated testing, so we lose automated and just say testing. So instead of eyeballing some output, the test code does it for you and runs every time you change your code. If something breaks, you know immediately. Today, we will see how testing ensures that our code works correctly and continues to work correctly as we make changes. It gives us the confidence to refactor and improve any code base without fear of breaking things. The same confidence carries over to letting AI make changes to our code, which matters as more and more coding is done with AI. We will also see how AI can accelerate the testing process itself. Testing has a long history in software, but in data roles, it isn't emphasized as much as it should be. When a web app has a bug, the app crashes and someone notices. But a bad join in a pipeline produces plausible but wrong numbers, and nobody catches it for months. Traditional software validates data on the way in and trusts it on the way out. Data work is different. You're frequently reading data you didn't produce, from sources you don't control. The prevalence of silent failures in data work is what makes testing even more important. The primary goal of keeping data in traditional software is to serve the application, not to build a prediction model or train large language models on it. But if you're working in a data role, your primary job is to analyze, interpret, and model messy and rarely structured data. We will see why testing data quality and modeling matters a lot. In this channel, we bridge the gap between writing Python and shipping production-ready Python, covering the essential ideas and tools you need to get there. We start with the same example we used at the end of the typing chapter. Here, the story is that a developer added a new customer tier, but accidentally entered 1.4 instead of 0.4 for the discount value. From the type checker's point of view, everything is valid. But from a business point of view, 140% discount doesn't make sense. And if we apply it, we get a negative price. So the code is type correct, but the behavior is still incorrect. This is a bug that type checking alone can't protect us from. Now let's see how testing helps us catch errors like this, not just this time, but also as the code base evolves. Your first instinct might be to test apply discount. Let's start by writing a happy path test. Python includes a built-in testing library, unit test, and the most popular third-party testing framework is pytest. This won't be a tutorial on either of them, except for one small pytest feature we will use. Let's run our test with pytest. This is a good starting point. The test checks that the function behaves correctly in a normal case, but it doesn't protect us from the bug. In order to catch the bug, we add another test. The test failed, and that's a good thing. Pytest is telling us that there's a problem with the diamond tier, which makes it easier to debug and fix. But notice that pytest says collected 2 items. The second function loops over all 5 tier members, so it actually makes 5 assertions inside a single test. If diamond fails, the loop stops there, and we never learn whether the other tiers would also have problems. Pytest has a very simple way to break this down with the parameterized decorator. Instead of using a for loop, we tell pytest to run the test function once for each tier member as a separate test case. Now we can see there are 6 test cases. 1 happy path test plus 5 parameterized ones, 1 for each tier. With the verbose flag, we can see each tier tested individually. Now, our code has some tests, and that's really important. There are still 2 things we can improve though. In our code base, it's very likely that other functions or methods also use the tier enum we defined for discounts. That means they can have problems similar to the one we have here. Should we go ahead and write more tests for those cases to catch the same bug? We could, but that would be extra work we can avoid. If we step back for a moment, the real bug isn't in apply discount logic. The apply discount function is doing exactly what we told it to do. It multiplies the price by 1 minus the discount rate. The real problem is in the data. Diamond has a value of 1.4, and that doesn't make sense as a discount rate. In this case, the better test is to go directly to the source of the problem and test the tier values themselves. This test catches the bug where it was introduced, and it doesn't depend on any downstream function. That gives us a useful general principle. Test the thing that's wrong as close to the source as possible. Let's fix the bug now so our tests pass. At this point, you might ask, are these enough tests? Are 2 tests too few? How would we know? Coverage tells us which parts of the code were exercised by our tests. In Python, the coverage library reports statement coverage by default, and it can also measure branch coverage. Let's run coverage on our tests. We have 100% coverage, which means every statement in our code was executed while the tests ran. Surely, that means we're well covered. You can't get more than 100% coverage, right? What are you going to do? Write tests for code that hasn't been written yet? Well, actually that's a thing, and it's called test-driven development. But TDD is a topic for another time. Despite having 100% coverage, we're actually still not well covered, which brings us to the second issue we mentioned earlier. What if a developer entered a negative discount? The discounted price would become larger than the original price, which is a bug. But our tests currently don't catch this. Like before, the source of the problem is the tier data. So we update our test function that would catch it. This helps us understand that coverage is good for finding untested code, but it isn't very useful as a single number that tells you how good your tests are. In a way, we have translated the question, how many tests do we need, into something a little more tangible, like what percentage of statements should be covered by our tests. That's still useful progress. In many code bases, you will see something like 80% coverage used as a minimum requirement. There are also great teams that don't enforce a lower bound because a coverage target can be easy to game, especially now that boilerplate tests are easy to generate with LLMs. What matters more is the quality of the tests. Since 100% coverage may not be enough, there's no single ideal number. Even at 100% coverage, we can still miss edge cases, so testing needs to be thought through carefully. Teams should choose targets that fit their risk level and business needs. So, if coverage alone isn't enough, and you should think about testing carefully isn't exactly easy to act on, is there any low-hanging fruit we can pick? The next thing people often reach for is mutation testing. Mutation testing asks a tougher question. If I make a small change to the code, do my tests notice? There are libraries such as mutmut that can do this for you. For example, imagine a mutant changes the applied discount logic. If your tests still pass, that's a red flag. This means that your tests weren't really checking the behavior closely enough. In our case, the happy path test catches it. The mutant was killed, so our tests are sensitive enough to detect this kind of change. Earlier, we stated a property that the discount tier should satisfy and tested it. Similarly, apply discount has properties it should satisfy. Since our tier values are valid discounts between 0 and 1, for any positive price, the discounted result should also stay strictly between 0 and the original price. Because the discount tier has a small fixed set of members, we could test the property for every value. But apply discount also takes a price argument, which makes the input space too big to test exhaustively. That's where we can go one step further with the hypothesis library, or more generally, property-based testing. You describe your hypothesis or a property that should hold for many inputs, including edge cases you may not have thought of. This test doesn't hard-code a single example. It expresses a rule that should always be true. Let's run it. It failed, and we didn't write that test case. Hypothesis generated it. The price 5e-324 is a subnormal float, the smallest positive value IEEE 754 can represent. At that scale, when we apply the discount, we round back to 5e-324 because the result is too small to represent with any more precision. So the strict less than price assertion fails since the discounted price equals the original. We can disallow subnormal floats in the strategy. It failed again with a different input. This time, hypothesis tried infinity. Infinity times anything is infinity, so apply discount with infinity returns infinity, and infinity less than infinity is false. We disallow infinity too. Pytest reports 7 tests here, but that last hypothesis test is actually exercising many generated inputs under the hood. Hypothesis kept finding edge cases in the float space until we constrained the strategy enough. This reveals a real problem in our code. Accepting any float as a price without validation is dangerous. We will talk about parsing and validation in the next chapter. So far, everything we have talked about comes from the world of everyday software development. It's worth noting that there is a much stricter standard in safety-critical systems that's called mcdc, which stands for Modified Condition Decision Coverage. If you're building flight control software, medical devices, or autonomous defense systems, regulators may require mcdc. So if you plan to work in defense tech or at a dual-use company, take notes. The idea is that executing every statement or branch isn't enough. You need to show that each individual condition in a decision independently affects the outcome. Here's an example. Now suppose you write these 2 parameterized tests. Those tests give you 100% statement and branch coverage because both the true and false paths run, but they don't satisfy mcdc. Why not? Because both conditions changed at the same time. Neither condition has been shown to independently flip the outcome. To satisfy mcdc, you add the missing test vectors. Now each condition has been shown to independently flip the result. mcdc also requires completeness. Each condition must take both true and false values across the test suite. Our 3 vectors satisfy that too, since isArmed and safety key inserted each appear as both true and false. Every test we wrote so far was for small pieces of our code in isolation, which are called unit tests. How do we test our code at larger scales? For example, to check how different parts of our system work together. To answer that, let's look at the different kinds of testing and how they relate to each other. The different kinds of testing are usually shown as a pyramid with 3 layers. At the base are unit tests. As we saw, these test individual functions or methods in isolation, or more generally, the smallest units of code. What counts as the smallest unit isn't always obvious. A useful rule of thumb is to think of it as the smallest piece of logic that does one coherent thing, such as making a decision, transforming data, or applying a rule, and can still be tested on its own. Unit tests are fast, small, and relatively cheap to write and run, so they usually make up the largest portion of your test suite. The middle layer is integration tests. These verify that multiple components work together correctly. For example, that might mean testing a function that reads from a database, a service that calls an external API, or a pipeline that pulls data, applies transformations, and writes the resulting features to a feature store. These tests are slower and broader than unit tests, but they are valuable because many production failures happen at the boundaries between components. At the top are end-to-end tests, or E2E for short. These simulate real user workflows across the entire system. For example, that might mean testing that a user can complete a checkout flow from start to finish. In an LLM application, it could mean testing the full path from a user question to document retrieval, prompt construction, answer generation, and finally showing that answer in the UI. These tests are the slowest, broadest, and most expensive to maintain, so you usually want fewer of them. There are many other types of tests. We focus on unit, integration, and end-to-end because they map to increasing scope and cost, and they build the right intuition for everything else. Let's see what integration testing looks like by returning to clean text. Earlier, we said there were more bugs hiding in it. The phi ligature isn't actually a bug. Casefold already decomposes it. The real issues are subtler. Cafe can be encoded as a single character or as E plus a combining accent, and our function treats those differently. The fix is Unicode data.normalize with nfkc. There's also an ordering bug. Collapsing whitespace before removing punctuation leaves double spaces, and punctuation removal can leave leading and trailing spaces. Swap the two regex lines and move strip to the end to fix that. Here's the corrected version. In a real system, clean text doesn't exist in isolation. For example, clean text could be flowing into an encoder, and the encoder would then write vectors to a database. Integration testing checks that these components work together across boundaries, not just individually. If an integration test fails, you know the pipeline is broken, but not which component caused it. Take two strings that look different, but should produce the same result after cleaning. Both go through clean text, then through an encoder. If cleaning works correctly, both produce identical vectors. When an integration test depends on external systems like a database or an API, you can use mocks to simulate them. Python's unittest.mock library with mock and magicmock is the standard tool for this. An end-to-end test has the same idea, but would go further. For example, you might test the entire flow from raw input in, cleaned and encoded, stored in a database, vectors used for RAG, and the user sees the result in the UI. One difference from integration tests is that you would do this with no mocks unless absolutely necessary to test the real system as closely as possible. Test behavior, not implementation. Don't test that casefold was called. Someone can implement the same behavior differently. Think of it as given, when, then, without referring to the implementation. Given some setup, when I run the function, then I expect this output. No need to test built-in or popular third-party libraries. They already have large test suites and are battle-tested by millions of users. Test how your code uses the libraries and integrates with them. We did this with clean text by testing the output of our function, not whether re.sub or casefold work correctly on their own. When you start working on an untested codebase, write a couple of end-to-end tests first. They catch big breakages immediately. Then, as you work on specific parts, add integration and unit tests before modifying the existing code. This flips the pyramid, but it's a pragmatic approach. Label your tests by type. Unit tests should run frequently, like on every save, every commit, every push. Integration and end-to-end tests are slower and often depend on external systems, so you usually run those only in CI. Pytest markers make it easy to select which tests to run locally and which to leave for the pipeline. Use AI to accelerate testing. Developers have always hated writing tests because it's boring, repetitive work for most. Now AI can draft a solid first set of tests pretty quickly. Tell it what kind of testing you want. If you ask for coverage targets, mutation testing, or property-based testing by name, the results are much better than just saying write tests. Be careful when testing floating point values. We saw hypothesis catch subnormal floats and infinity in our pricing tests. The same issues come up constantly in data work. Previously, in the typing chapter, we added type annotations to catch bugs that testing alone wouldn't catch. Today, we learned about adding tests to verify correctness and catch the kind of bugs that type checkers can't see. Together, typing and testing catch most issues in our own code before they reach production. But in real systems, a lot of the data comes from sources which we can't fully control. API requests, config files, CSV uploads, user input. Nothing stops someone from sending price 0 tier diamond to your endpoint. We spent an entire chapter hardening clean text, but how do we even know the file we read to clean is a valid string? What if it's binary or truncated, or in an encoding our code doesn't expect? In the next chapter, we will talk about parsing and validation to complete what I call the typing, testing, and parsing holy trinity. We will see how to take raw, untrusted input and turn it into data our code can actually rely on. See you there.